Another thing you can do with Cayley-Milgram is you can use it to rederive Hall's marriage theorem. So less obviously, Hall's marriage theorem can be proved again using Cayley-Milgram. Here is how it works. Recall what the static is. You have a bipartite graph GXY that satisfies the Hall condition, by which we mean that we have the number of neighbors of a set A is at least the size of A for each subset A of X. We must prove that, well, we must find an X-complete matching of G. So first of all, you have to turn your graph into a digraph because Cayley-Milgram requires a digraph. How would we do it? Here is the obvious way. You start with G and you direct each edge from X to Y. So that it goes from X to Y. In other words, each edge with endpoints X and Y becomes an arc with source X and target Y. So let me draw this, or try to draw this. You have the two sets X and Y. And you have a bunch of edges that go between the sets. And each of those edges you turn into an arc that goes from the left vertex to the right vertex. That's how your graph becomes directed. So what you get, of course, is not a random wild directed graph. It's a pretty simple graph that is pretty tame. So namely, this digraph D has a special property. Any path of D has length at most 1, because you can only go from a vertex X in an X to a vertex in Y. Once there, you cannot go any further. Thus, a path of D corresponds either to a vertex of G or to an edge of G. Hence, a path cover of D necessarily consists of vertices and edges of G, and moreover, the edges of this path cover form a matching of G, because in a path cover you cannot have two paths containing the same vertex. And the vertices are precisely the vertices that are not matched by this matching. Now, the Cayley-Milgram theorem gives us a path cover P of D and an independent crosscut S of P. Remember, a crosscut means an independent set. Well, it means a set that contains exactly one vertex from each path in P, and it has to be independent in our case. Consider this P and S. So let me draw this, and I will draw it in a convenient way. I will put the arcs that are, so all the paths of length 1, I will put on the bottom, and all the paths of length 0, I will put on the top. So my path cover is going to look like a bunch of length 1 paths and a bunch of length 0 paths. And because I can choose how I draw my digraph, I choose it in such a way that all the length 1 paths are at the bottom and all the length 0 paths are at the top. So this is P, the path cover. Now, how does the independent crosscut look like? Well, it's a crosscut. So from each path you choose one vertex. In case of the length 0 path, that's obvious what you do, because there is only one vertex on each path, so you have to choose that one vertex. So all of these unmatched vertices, you have to choose, they have to belong to S. Whereas in the matched part, so in the part with the length 1 path, you have to choose one vertex from each path. So for example, you can choose this vertex, or you can choose this vertex. Let's do the second. Here, let's again do the second. Here, let's do the first one for variety's sake. And here, let's again do the second. So this is how S should look like. Of course, sometimes you have more vertices on the left, sometimes you have more vertices on the right. Anyway, let's draw some consequences. We observe that n of x intersection S is a subset of y without S. Why is this true? Well, the set S is independent, so we have clearly a neighbor of a vertex in S cannot be in S. So a vertex, if you have a neighbor in X intersection S, then you have to be out of S. However, I claim that you actually have to be in Y without S. And why are you in Y? Well, because you have a neighbor in X, and the graph is bipartite. So any vertex with a neighbor in X has to belong to Y. And therefore, of course, a subset always has size, at most the size of the original set. So you get this here. And thus you have this greater or equal to this. And by Hall's condition, by the Hall condition, the number of neighbors is at least the number of elements. So if you look at the set Y, of course, it is the size of Y is the size of Y intersect S plus the size of Y without S. That's just set theory. And we have just said that this is at least the size of X intersect S. So you get this plus this. And this is, of course, the size of S, because S is the union of its two disjoint subsets, Y intersect S and X intersect S. Okay, now let's think about it. So this crosscut, so this green set, has size at most the size of Y. This is what this inequality is saying. The size of S is less or equal to the size of Y. This means that, so speaking pictorially, it means that there cannot be any unmatched vertices in X. So in other words, this brown stuff does not actually exist. Why not? Well, imagine that it does exist. So you have, let's say you have P vertices here. Similarly, you have Q unmatched vertices on the right. Let me make them red. And you have, oh, okay, so they're also brown. And finally, let R be the number of arcs, so the number of actually matched edges. So let me call it R. So if this is the case, then let's just compute what things are. The size of S is going to be P plus Q plus R, because if you look at the green vertices, each of the P brown vertices is green, each of the Q vertices is green, and each of the matched edges has exactly one green vertex. On the other hand, the size of Y is Q plus R, because in Y you have the unmatched elements and you have the matched elements whose number is the number of matched edges, which is R. So if the size of Y is to be greater or equal to the size of S, as we have here, then Q plus R has to be greater or equal to P plus Q plus R. And this is only possible if P is 0, which means this brown stuff on the left doesn't actually exist. And this means every vertex in X is matched. So this easily yields that our matching consisting of the edges that form the length 1 path in P matches. So what is the right way to say? Our matching matches all vertices in X. In other words, it is X complete. Thus, we have found an X complete matching, and Hall's marriage theorem is proved.